Correlation. One issue with using covariance as the measure of a relationship is that it's going to be scale dependent, meaning that if we add a 0 to all our measures, the covariance is going to change, which means that we cannot compare covariance numbers between different relationships. And that's why we usually want to use correlation when we describe a relationship between two random variables. So let's look at the relationship between the weight and the height of individuals in the US. So this is just a small sample, male and females, of their weight and their length. And as we note, the more you weigh, the taller you tend to be. So we have a positive relationship here. So the red line is so-called trend line, which is just telling us which direction is this relationship going. So if it's positively, meaning it has a positive slope, it means it's a positive relationship. Note down in the right corner, we have calculated the covariance of this sample and the correlation of this scatter plot. So we notice the covariance is positive, the correlation is positive, which means that it's a positive relationship here. Now we're going to change one thing, and that is that instead of measuring the weight in kilograms, I'm going to measure the weight in pounds instead. And what we're going to note is that everything's going to be the same, except that the covariance is going to change. So the only thing that's going to change now is that the covariance now is 203 instead of 98. And this is the issue with the covariance, is that the figure is exactly the same, the slope of the trend line is exactly the same, the relationship is exactly the same, but the covariance just changed. But the correlation is still 0.77. So that means that the correlation, we can actually use that and compare relationships between different random variables. The correlation between two random variables is often denoted with the Greek letter rho. And the definition is that we take the covariance and then we just standardize the covariance with the respective standard deviation of the random variables. If we do that, we know that this measure will always be somewhere between -1 to 1, which means that the more positive and the closer it gets to 1, the more positive relationship we have. The more negative and closer to -1, the more negative the relationship gonna be. I also want to just quickly show three extreme cases when it comes to correlation. The first one is when we have a perfect positive correlation. So in this case, we have two random variables, x and y. These two random variables has a correlation equal to 1. When we have this set up, it means that whenever one variable increases, the other one will always increase also. And the relationship always going to be the same. So that means that if we know how one of these variables is moving, we know exactly what's going to happen to the other random variable. This particular case has a special name. This is so-called perfect positive correlation. We don't even need the other variable. We only need to measure one of these variables because from one of these variables, we know exactly what's going on with the other one. The other extreme case is if we have a negative correlation and a negative correlation equal to -1. In this case, we call this a perfect negative correlation. So similar to how we know exactly what's going to happen with the other variable, if we know what's happening with one of them, the same thing is happening here. The only difference is that when one increases, we know that the other one will always decrease. So we have a negative relationship between the two random variables. The final, I don't know if I would call it the extreme outcome, it's probably the most common outcome you're going to get, and that is that there is no relationship between the two random variables. And that we're going to get when we have a correlation of 0, meaning that there is no obvious relationship between these two random variables. It's just a cloud of noise when you do a scatter plot. In most cases, we're going to end up somewhere in between -1 and 1. And then we're going to need to discuss, okay, what's a strong and a weak relationship? But whenever we do that kind of value judgment, we need to always compare it against something. Weak relative to what? Strong relative to what? There are just two notes here I want to make that is very important when it comes to correlation and relationships overall. First of all, the correlation is a linear relationship. So if we have a non-linear relationship, meaning that in this example, we might observe that we have a negative relationship for low values of x, and then we have a positive relationship for large values of x. When we have this kind of non-linear relationship, the correlation variable, the correlation value, will lie. Because the correlation gonna assume there is a linear relationship, which means it's just the average slope. But in this case, it might trick us, because In this case, if we have a very low value of x, for example -2, then we're actually going to have a negative relationship. So it's going to change depending on what value we observe. In these cases, the correlation will be a poor measure of the relationship. The other thing that is much more important is that correlation is not causation. And this is so important. And it's so easy to mess up. Even people like me who has worked with this a lot, it's very easy to run into this issue. Just because there is a relationship doesn't mean that one variable causes the other one. And in most cases, everybody is gonna nod here and like, yeah, obvious. It's like, yes, we just have a relationship. Of course, it doesn't mean that there is a causation. And just to point this out, let's revisit the weight and the height. Most of us will understand that if I want to get taller, I will probably not get taller by just eating more. I'm just gonna get more girth instead of length. And most of us understand this. So there's a relationship between the weight and the height, but it doesn't mean that weight causes you to gain length. All right? So that means that correlation is not causation. However, if you have ever listened to a political debate or reading media newsletters, you're gonna realize that most people mix these up. Just because there is a relationship doesn't mean that there need to be a causation. So it's very hard to show that X causes Y or Y causes X. It might also be that we have some Z variable that causes both of these to move in the same direction. Or maybe they just randomly happen to go in the same direction. And this is very, very important distinction, and I can't emphasize this enough. Correlation is not causation. A relationship doesn't mean that there must be a causal link between the variables. So just keep that in mind whenever you hear a politician start talking about statistics or a relationship. Are they talking about a correlation or are they making a causal argument? And if they are making a causal argument, then the evidence needs to be much stronger. So, correlation. It's a linear relationship. The nice thing with correlation is that it doesn't depend on the scale, meaning that we can use the correlation number from one relationship and compare it to another relationship. If you have a higher score, it means it's a more positive correlation. It's a more positive relationship between the two variables. The more negative it gets, you get a negative relationship, which means that when one increases, the other one has a tendency to decrease at the same time. And remember, correlation is a linear relationship, and more importantly, correlation is not causation.